Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In this video, we will be dealing about a part of hydrocarbons called as alkanes. Okay, so hydrocarbons are broadly divided into two categories. One is saturated hydrocarbons and unsaturated hydrocarbons. All the singly bonded compounds they fall under saturated hydrocarbons, and all the double and triple bonds they come under unsaturated hydrocarbons. So alkane belongs to a class of saturated hydrocarbons. Okay. So, alkanes are the simplest organic compounds made up of carbon and hydrogen only. They have the general formula CnH2n+2. The carbon atoms in their molecules are bonded to each other by single covalent bond. Since the carbon skeleton of alkane is fully saturated with hydrogen bonds, therefore they are called as saturated hydrocarbons. Okay, alkane contains strong carbon-carbon and carbon-hydrogen bond. Why? Because they are sigma bonds and they are mostly formed by head-on overlapping. Okay, therefore they are stronger bonds. Therefore, this class of hydrocarbons are chemically inert. Okay, they do not react with organic compounds or reagents that much. Hence, they are sometimes referred to as paraffins, which means little affinity. The first three members are shown as methane, ethane and propane with carbon number 1, 2 and 3. Now, if I look at the structure of hydrocarbon or structure of alkanes, there the carbon atom is present at the center and the hydrogens are directed towards the four corners of a regular tetrahedron. Therefore, alkanes basically have a tetrahedral geometry. Okay, they have a tetrahedral geometry. Now, in methane, the carbon atoms form single bond with four hydrogen atoms. All the hydrogen-carbon-hydrogen bond, the bond angle is basically 109 degrees 5 minutes. Methane has a tetrahedral structure and the carbon-carbon and carbon-hydrogen bonds, they are formed by head-on overlapping of sp3 hybrid orbitals of carbon and 1s orbital of hydrogen. Okay. Now, we will see some methods of preparation of alkanes. First is, they are mostly naturally found in marshy or dampy areas. Okay, as you can see, the biogas plant, it mostly consists of methane and ethane, right? So, naturally, they are synthesized by decomposition of plants and waste matter. In laboratories also, they can be prepared by different methods like from unsaturated hydrocarbons, from alkyl halides, by reduction of alkyl halides, by the use of Grignard reagent, and from carboxylic acids. These are certain ways by which we can synthesize alkanes in the lab itself. Okay, now let us see these lab methods one by one. The first is from unsaturated hydrocarbons, mostly alkene. Now, if to alkene I add a molecule of hydrogen, this method involves by hydrogenation or addition of hydrogen. This is that's why it is called reduction. That means reduction basically means addition of hydrogen. So, in this method what happens, if I am seeing a general reaction, this is my ethene with a double bond, I am reacting it with hydrogen in the presence of a metal called nickel or any nickel, palladium, platinum, any inert metal. Okay. Then what happens, this hydrogen molecule basically adds up to the ethene, breaking one pi bond and they result in the formation of ethane. Okay, a special reaction occurs when we use Raney nickel. Here we were using only metallic nickel. Now, if we take up the nickel and activate it with 50% nickel and 50% aluminium, we get Raney nickel. In that, in the presence of Raney nickel, if we carry out this hydrogenation reaction, it has got a special name called as Sabatier-Sandurance reaction or reduction. This is basically a name reaction. Now, if I look at the general reaction, it somewhat looks like this. Ethene plus hydrogen in the presence of Raney nickel gives rise to ethane. The next method is from alkyl halides. Now, this method can be used for the preparation of alkene from alkyl halides by, first is Wood's reaction, second by the use of Grignard reagent, and third by the decarboxylation reaction. Okay, means reduction of alkyl halides. So, first is the Wood's reaction. In this, two molecules of alkyl halide, they react with sodium in the presence of dry ether. Okay, dry ether is the medium in which this reaction is carried out. The general reaction somewhat looks like this. Okay, two molecules of alkyl halide, they react with 2 molecules of sodium, then there is liberation of 2 NaX. X may be any halogen, chlorine, chlorine, bromine or iodine. After the liberation of that halogen, we get 2 moles of alkane. Okay. Here, what is the use of dry ether? Dry ether is used to keep sodium atoms dry, because sodium, when reacts with water, it is highly explosive. Okay, so that it does not catch fire in moist condition. If there is any traces of water in the reactant medium, then basically that moisture is absorbed by this dry ether. What is the limitation of this reaction? Here, first thing is, we need to take the same alkyl halides, otherwise we will get a mixture of alkane. What will happen? Alkanes basically have the same boiling point, melting point, both basically same physical properties. So therefore, it will become very difficult to separate the alkanes from each other. Therefore, we need to take the same alkanes only. And next limitation is, it is only used for the preparation of even number of carbon atoms. Okay, alkanes with even number of carbon atoms. The next is by the use of Grignard reagent. Now, the Grignard reagent is a class of organometallic reagent. What do you mean by organometallic reagent? A reagent which has a organic part as well as metallic part. As you can see here, its general formula RMgX. Here, R is the organic part and Mg is the metallic part. So therefore, it belongs to a class of organometallic reagent. And if the metal is magnesium, particularly magnesium only, then the reagent has got a special name called Grignard reagent. Okay. Now, how Grignard reagent is prepared? If alkyl halide is reacted with magnesium in the presence of same dry ether, we get RMgX. Now, when ethyl bromide reacts with magnesium, we get ethyl magnesium bromide. Next, when we add water, what happens? This bond breaks, addition of hydrogen to CH3CH2 and OH2 MgBr, we get our ethane. Okay, the reaction somewhat looks like this. Now, by decarboxylation reaction, which means removal of carbon dioxide. Okay, decarboxylation means removal of carbon dioxide. In this, first the carboxylic acid is made to react with sodium atom, so that it forms a salt of carboxylic acid. Next, it reacts with soda lime to get our desired alkane. For example, if I am taking acetic acid, it reacts with sodium, you get sodium acetate, salt of acetic acid. Now, when this salt of acetic acid reacts with soda lime, you get your alkane methane, CH4, with the liberation of Na2CO3. Now, from this molecule, a carbon dioxide has been liberated, therefore the name decarboxylation. Now, if I see some of the physical properties of alkane, first is polarity. Now, as alkanes consist of same kind of atoms, therefore they are non-polar. Okay, alkanes are mostly non-polar because the electronegativity difference between carbon and hydrogen is nearly same. Next is existence. Now, the force of attraction present in them is van der Waals forces, due to which lower members, that is C1 to C4, they mostly exist as gases. C5 to C7, they mostly exist as liquids, and the higher ones, they exist as solids. Now, if I say boiling point, obviously they are non-polar, therefore the force of attraction between them is very weak, van der Waals. So, if I compare other class, they will have generally low boiling point. Okay, the boiling point, but however it increases with increase in the number of carbon atoms due to increase in van der Waals forces of attraction. However, with increase in branching, the surface area decreases and hence the van der Waals force also decreases. Therefore, boiling point also gradually decreases. Therefore, butane has more boiling point than 2-methyl propane. Okay, because here branching is observed. Okay. Now, if I take up melting point, again melting point depends mostly on symmetry. If the molecule is symmetrical, then it will fit to the crystal lattice better, as a result of which the melting point will be higher. If the molecule is non-symmetrical or unsymmetrical, then the crystal lattice will not be like perfect fit, there will be distorted, therefore the melting point will gradually decrease. Okay, so melting point, it not only depends upon the mass but also on the structure of hydrocarbon, mostly on the symmetry. For symmetrical or even number of hydrocarbons, it is higher, and for odd number, it is lower. If I say solubility, now solubility means dissolution with water, dissolution with a polar solvent. So if they are non-polar, like dissolves like, that means water is a polar solvent. Therefore, alkane will be less soluble in water but more soluble in non-polar organic solvents like CCl4, carbon tetrachloride. Okay. Now, if I see the chemical properties of alkane, what chemical properties? First thing, they are very less reactive because they fall under the category of paraffins, having little affinity. The whatever chemical reactions they are showing with a great difficulty. So, what are those reactions? The first is substitution reaction. Now, substitution reaction, in this, one or more hydrogens are replaced by other atoms. For example, halogenation. In this, substitution by halogen X, which might be fluorine, chlorine, bromine or iodine occur. And if I see the reactivity, then fluorine will have the highest reactivity, then chlorine, followed by bromine and iodine. Out of them, chlorine shows this reaction at an efficient level because with fluorine the reaction is very fast, and with bromine and iodine comparatively the reaction is very slow. So the efficient reaction is shown with chlorine. Okay. So we'll see the chlorination of methane. This reaction occurs in the normal light or UV light, you can say. Okay. Now this is the reaction. Methane reacts with chlorine in the presence of light. It forms chloromethane. Now it has further scope of removal of hydrogens. Like this reaction will continue till all the hydrogens in methane are replaced by chlorine atoms. So finally what you will get? Carbon tetrachloride. And in the third step you will be getting a very important compound called as chloroform. Okay. Next reaction. Okay, this is the mechanism of this reaction. First of all, what happens? This is basically a chain reaction. Okay, the chain follows until all the hydrogen atoms are completely replaced. So in the first step, what happens? It is called a chain initiation reaction. Here, free radicals are generated. The chlorine gas breaks up into chlorine free radical. Now this chlorine free radical provides a strength for the further reactions. So in the second step, what happens? Chain propagation happens. Here methane reacts with chlorine free radical to form, one is methyl free radical and HCl. This methyl free radical combines with the chlorine free radical to give you methyl chloride. This process goes on continuing. In the chain termination step, what happens? Methyl chloride is formed. Now another chlorine free radical is generated. Two chlorine free radicals, they combine with each other to give you the chlorine gas, and two methyl free radicals, they combine with each other to give you ethane. Okay. This is basically the mechanism of the reaction. Next is controlled oxidation. Now this occurs in the presence of a catalyst, and on the basis of the catalyst the products are formed. Basically this reaction, oxidation, depends upon what catalyst I am using. So first of all, if I am using copper catalyst at 523 degree Kelvin and 300 atm, then I will get alcohol, methanol. Now if I am using molybdenum oxide, MoO3, then I will get aldehyde, methanol. If I am using silver oxide, then I will get methanoic acid. Okay. So controlled oxidation occurs in the presence of a catalyst, and the catalyst is the judgmental factor on for the products formed. Depending upon the catalyst only, the products will differ. Next is isomerization reaction. Now what happens? If we subject alkanes to anhydrous aluminium chloride, AlCl3, then isomers of alkanes are formed. First, if butane is subjected to reaction with anhydrous AlCl3, it will form 2-methyl propane. Okay. Next is the aromatization. Aromatization means cyclization. So what happens if hexane is reacted with vanadium pentoxide at 773 Kelvin and 10 to 20 atmospheric pressure, you will get mostly benzene. Okay. Benzene plus hydrogen will be removed. Okay. So this was all about the chemical reactions of alkanes. Here we put an end to the properties, preparation as well as properties of alkane. I hope you are clear with the chapter. In the next video, we will be taking up alkenes. That's all for the video. Thank you so much.